Welcome back. Last lecture, we started talking about this general framework called the Primal Dual algorithm. And we're going to go over that now and also show a few of its properties. And this will set the stage for subsequent lectures where we will be applying this the Primal Dual technique. Let's briefly recall the basic setting and what we had discussed in the previous lecture, so that we have everything that we need to move forward. So the basic setting is as follows. We start with a dual variable. Let's write down the main idea first. So the main idea is that if complementary slackness holds for two feasible solutions, for a primal feasible and dual feasible solution, then we're in business. So this motivates the idea, given a dual feasible variable, can we find a primal feasible variable that satisfies complementary slackness? That's the first idea. And if the answer happens to be yes, we know that by strong duality and complementary slackness results that we've showed, that this is a certificate that this is a primal dual optimal pair. But the real power of the primal dual algorithm comes from the fact that if the answer is no, if we do not have if we're not able to satisfy complementary slackness, then we can improve the dual solution. So it really is like a dual algorithm. It is constantly maintaining dual feasibility while improving the solution. So very quickly, okay, so the idea is use complementary slackness. If there exists an X which satisfies complementary slackness with our dual variable, dual feasible P, then we know that XP are optimal pair. Otherwise, we can improve P. So again, very, very briefly, this is how it works. Step one is we start with a dual variable. Actually, let's just quickly, just so we have everything on one page, let's write down the primal and the dual. So remember the primal, I'm squeezing it in here. It's minimize C transpose X. It's in standard form, subject to AX equals B, X non-negative. And then the dual is maximize P transpose B, P is the dual variable, subject to P transpose A less than or equal to C, and otherwise P is free. So the primal dual framework says start with a dual feasible P and use this to define a restricted primal whose only goal is not going to be to minimize the objective. C is nowhere present here in what we're going to see going forward, but it's just to satisfy complementary slackness. So the key things here are J, which is the set of admissible columns, all J's such that P transpose AJ is equal to CJ. These are the only indices of X which are allowed to be non-zero, and therefore this allows us to define the restricted primal, which is minimize. Oh, there's another comment that I should make. It's in the slides of the previous lecture, but I had not stated it explicitly. Note that without loss of generality here, we can take B to be non-negative. I just introduced the required negative signs into A. As a minor point, but if you follow the details, you'll see where this is needed. So we're going to minimize the sum of some auxiliary variables that are added purely to guarantee that this restricted primal is feasible, subject to, I'm going to use my shorthand notation, aj xj. So I basically have not just set to 0 the elements of x that are in j complement, but I've also just removed those columns from A, plus the auxiliary variables equals b. So note that this guarantees that I have a feasible solution. The fact that b is non-negative without loss of generality allows me to say that these variables must be non-negative. And similarly, the variables in xj are non-negative, because anyway, all the x have to be non-negative, but the variables in j complement are required to be equal to 0. This is called the restricted primal, and the dual to the restricted primal then reads maximize P transpose B subject to P transpose AJ less than 0 for every admissible J. J in J. And note again, this is 0. C is gone. This is why we say we combinatorialize the cost in this framework. P is less than 1 component-wise, and otherwise P is free. So do this exercise if you didn't already to make sure that you know where this dual comes from. Where are the new elements? Why is this 0? Why is this 1? Etc. Okay, so this, as we mentioned, if we solve the restricted primal with simplex, we also get in the solution the solution to the dual restricted primal. And if we call P bar the solution to the dual restricted primal, then, as we explained in more detail last time, we update our dual variable by writing that P new is equal to P plus theta times P bar. So what happens here? Theta is determined by looking at which new constraint is going to become tight. Again, very, very similar to the spirit of simplex method itself and the tableau when we introduce a new column into the basis and it zeroes out one of the basic variables, one of the elements already in B. That's what exits the basis. Here something similar happens. J is the set of tight constraints in the dual. We find this P bar, we move in that direction until a new constraint has become 0. And that's how theta is determined. We gave those details last time. And also we saw that if the restricted primal has a strictly positive value, which it will unless we found a dual, unless we satisfy complementary slackness, in which case we stop, then by strong duality, the dual restricted primal, DRP, is going to have a strictly positive value. And therefore, P new is going to be strictly better. In other words, P new transpose B is going to be strictly greater than P transpose B. Again, just to finish this P is determined by I'll just write the expression by looking at minimum over J in J complement such that P bar transpose AJ is positive. Note that P bar transpose AJ is less than or equal to 0 for any J that's in the set of admissible columns in J, but this is in J complement. And then it is, what we've got is CJ minus P transpose AJ divided by P bar transpose AJ. And you can just check for yourselves that if you set theta to this value, that means that a new constraint in the dual is going to be satisfied tightly. All right, this is our framework. And now what we're going to show in this lecture is a few properties of the primal dual algorithm, and also in particular, just review why from simplex and from basic geometric facts that we know about polytopes, this is guaranteed to terminate at some finite time. It cannot go on forever. Okay, so a few properties of the primal dual algorithm. I'll just write these as a theorem. So first one is straightforward. If the value of the restricted primal is strictly positive, by strong duality, this means the value of the restricted dual is strictly positive. And if P transpose AJ is less than or equal to 0 for every J, not just the J in the set of admissible columns. That's enforced by DRP. Let's flip back to see. That's this constraint here. So what this theorem is saying, and the hypothesis is, if this inequality, P transpose AJ, is less than or equal to 0, holds for all J, then dual is unbounded, which means that primal is infeasible. Not just that we can't get complementary slackness, but it's infeasible. And this really follows directly from what we said on the previous slide. If P transpose AJ is less than or equal to 0, then you can let theta go to infinity, and the new cost of the dual is going to be P nu transpose B, which is P plus theta P bar, all of that transpose B. But we know that P bar transpose B is strictly positive because that's exactly this statement plus strong duality. Okay, so we've got that. Here is a more important, and this is perhaps slightly more subtle statement. And the next result tells us that there's a very nice computational convenience that we have by using the primal dual method with simplex. And namely that, what is the process? We start with P, we solve the restricted primal using simplex, then we update P, and then we solve the restricted primal again. This theorem says that every time we're solving and resolving the restricted primal, you can just start simplex in the previous, at your previous solution for that restricted primal. And in particular, it says the following. Let B be the basis, the optimal basis for the restricted primal. You ran simplex on restricted primal, you terminated, you have a B. So in particular, note that this means that B is a subset of the admissible variables, the only ones that were allowed to be non-zero anyway. Those are the only ones that are allowed to be in the basis. But also we had a bunch of auxiliary variables. So it's we had M auxiliary variables. So B is a basis of those. Again, if B is only a subset of J, then we stop because that means that all of the auxiliary variables are set to 0 and we've satisfied complementary slackness. So suppose that this is B. The statement of this theorem says that it says that the variables in J that are also in B, so that portion of J so that portion of B that's also in J, I guess I should write it that way. The portion of B, it's the same thing, but just perhaps more suggestive, that's also in J, is now also contained in the updated admissible variables. So simplex method is never going to terminate for restricted primal with a variable that's non-zero that does not remain admissible. So in other words, if some variable belongs to the basis and also to the admissible variables, which means that for our old dual solution, let me actually just write old here so it's even more clear. So we had this is what made it be part of J. Then when I update my dual variable, for that same j, I still have it equal to cj, which means it's a tight constraint in the dual, which means that it's going to be in j new. It's going to be admissible. Again, we can just use properties of DRP to see this. We know that P bar transpose AJ is less than CJ because of the constraints by design of but if J is in B, well, now we need to use this part. What do we know if J is in B? We also know that its reduced cost is 0. So and this is where we're using simplex. Its reduced cost in RP, not in the original primal, is 0. Sorry, this is this is not a CJ, of course. This is 0. This is what the constraint is here. So we know it's less than or equal to 0, but again, that's not enough. And so we know that P old AJ is equal to CJ, and now we know that P transpose AJ is less than 0. The assertion of this theorem is that it's actually equal to 0. And let's see why that's true. So it all follows because it's in the optimal basis. Its reduced cost is 0. What is the reduced cost in RP? So again, emphasizing, in RP, the reduced cost of J is equal to the original cost. But what is the original cost in RP? It's 0 minus P bar transpose AJ. And we know that the reduced cost is 0, which is the same statement as saying that P bar transpose AJ is equal to 0. And no, this follows. So again, what this tells us is that we can start the simplex method at the previous solution, and that is that's very useful for us. Okay, we're going to use all of these now to claim that the primal dual algorithm is finite. So in other words, it can't just approach the solution. It will terminate with the optimal solution or an assertion that the primal is infeasible after a finite number of steps. Okay, so let's so how do we see this? Let P, as usual, be the dual solution. Let's let, again as usual, P bar be the solution to the dual restricted primal. And I'm going to suppose that P bar transpose B is strictly positive. If it's not, then we stop and we're certainly finite. We're optimal. So I'll write that again. Else we're optimal and we stop. And assume that there exists some J that's not admissible with P bar transpose AJ strictly positive. And otherwise, P is infeasible and we stop. Again, you may want to make sure that you understand why this is the case. We've said that in this lecture. So theta is now equal to the minimum, which is non-empty by the above assumption, of J in J complement P bar AJ greater than 0 of CJ minus P transpose AJ over P bar transpose AJ. And let's call the winner of this j hat 0. So our choice of theta, so j0 is the argmin of this minimization. And what does our choice of theta guarantee? Our choice of theta guarantees that p nu times this j0 column. I guess I'm really writing down the details of what I had said in words in the previous slide. Again, p nu is equal to p plus theta times p bar times aj0. Our choice of j0, our choice of theta, guarantees that this is equal to cj. So now we have a different column that is admissible. So I'm going to write this as j0 is an element of j nu. So now let's look at what happens in the next iteration of restricted primal. So in the next iteration of solving the restricted primal, what has happened? Well, we have introduced this new column, and critically, the new column that we've introduced, which was not previously in the basis. Okay, so that means that this j0 is not in our old basis. And the previous slide told us that we were going to restart restricted primal from the basis where we were previously. j0 is not in that basis, and that new column is guaranteed to have a strictly negative reduced cost. Reduced cost of the new column j0 is cj0 bar. Again, it's equal to the cost in RP. Remember that all of the original variables are assigned cost 0 in RP. So it's 0 minus p bar transpose aj0. Why p bar? Because we said we're now restarting we're starting to solve RP using our previous solution, and our previous solution had p bar, c b b inverse. It had p bar, and because p transpose aj is strictly positive, negative p transpose aj is strictly negative. And what does this all tell us? This guarantees that we pivot. We're not going to stay at the same solution. So it's a pretty simple thought here that if you have an algorithm that is always pivoting and always eliminating negative reduced cost, as long as you can make sure in the face of, so first of all, let's take this slowly here. If no degeneracy, this implies that the value of the restricted primal strictly improves, so strictly reduces. And because we have only a finite number of extreme points, it means we have finite termination. That's the nice thing about simplex methods. Since you're going corner to corner, if you are strictly improving at every time, the algorithm must stop. Whereas for a different convex optimization problem, you can easily imagine a scenario where you're strictly improving, and you don't terminate. Or you converge to the wrong thing even. But if we do have degeneracy, we need to take care of, just to make sure that we never revisit the same basis. We haven't gone into the details of this in this class, but it is easy to accomplish this by adding a tie-breaking rule that's called an anti-cycling rule. So we may not improve the value, but if we have an anti-cycling rule, plus the fact that we have a finite number, possibly large, but still finite number of basic feasible solutions. Remember, two basic feasible solutions can correspond to the same geometric corner point. Again, implies finite termination. and that is the result that we want. So, in addition to going over the Primal Dual framework again, start with a primal, try to impose complementary slackness. If that fails, update. Start with a dual variable. If that's feasible, try to find a primal solution that guarantees complementary slackness. If that fails, we can improve P. This, in addition to describing that framework again, here we've shown a few things. One is that we can just restart. We can use simplex method and just restart at our old basis. And if we're using simplex method, and this is a bit subtle but a crucial point, if we're using simplex method, we're guaranteed finiteness. So it's important to look at that and realize that the finiteness here for this overall general framework is guaranteed just because we're using simplex method. If you use some other method, which we will in some cases, to solve the restricted primal or the dual restricted primal, then you need to come up with another guarantee of finiteness. But if you're willing to use simplex, then you're guaranteed that primal dual is a finite algorithm. So how are we going to use this? What's coming up next? What again we've seen at a high level is that primal dual combinatorializes. Our LP. And what this really means is we're going to be looking at graph problems, and some constraints are going to come from the topology of the graph. Those are combinatorial constraints. You can think of them as somehow being structural. Things that relate to things being on or off, or having to do with an edge being there or not edge being there is structural and is thus already combinatorial. On the other hand, if I have a cost of selecting a particular edge, or if I have a capacity of that edge, those could be rational numbers and are not combinatorial. So a cost to a particular edge is what we've been talking about effectively now. We've been talking about how to combinatorialize the cost function. If I have a capacity on an edge, then that is a right-hand side constraint. That's the B. And we need to think about how to combinatorialize that. And you can see that really we've already done that. If we want to combinatorialize the cost, then we start with a dual solution. If we want to combinatorialize the right-hand side, then we're going to take the dual of that and start from there. As we know, the dual and the primal swap objective function and right-hand side. So we've already done that. We're going to treat this in detail with two particular examples. So what we're going to do next is step back from primal dual for a minute and talk about the network flow paradigm, and talk about two specific problems, and then we're going to apply primal dual to those. So this is what we're going to pick up with on the next lecture.